Section 6.1, friction. Some people would say this section is a little bit rough, but others would say that it really helps them get some traction with the ideas of forces. So let's take a look at friction. So friction forces, it turns out, are essential. We use them all the time. If you're picking things up, if you're walking, biking, driving anywhere, writing with a pencil involves friction. Building with nails, weaving cloth, right? Stop and imagine for a moment if you tried to walk or drive with no friction. It would be like everything was icy, black ice, right? Super slick, and you couldn't get anywhere. There's this helpful illustration of a bookshop that has the friction section and the non-friction section. And none of the books in the non-friction section can stay on the shelf. So friction can actually be a pretty useful and important thing. I, for one, am glad that nails that get hammered into the building have friction to hold them in place so they don't just fall out. That would be a bummer. But it turns out overcoming friction forces is also important. The efficiency in engines, so 20% of the gasoline used in a car goes to counteract friction in the drivetrain, the part that's making things rotate. Roller skates, fans, those are things that we don't want a lot of friction. We want our fan to be able to just keep spinning. Same with the skates, we want to keep rolling on. So basically anything that we want to remain in motion, we want to be able to overcome this frictional force. So that's why this force is so interesting. It often gets a bad rep because it is something that needs to be overcome, but it is something that's also really useful and key to our everyday life. So let's think about 3 experiments, and you can try them out yourself. You could shove a book across the counter. You could push the book at a constant speed across the counter, or you could push a crate or another heavy object like the sofa or your desk that doesn't move. Push it on my desk, it's not going anywhere. So what's going on with each of these cases? Well, we can take a look. When we shove a book across the counter and stop pushing, the book is going to slow and stop, unless it's a super slick counter, right? So that tells us there's some sort of acceleration that's parallel to the surface and opposite the motion, that the book is not able to just keep traveling at a constant speed. The only time it can travel at a constant speed is if you're able to keep pushing on it. So even though you're pushing on it, it's not accelerating. So there must not be a net force, so there must be some opposing force that's equal and opposite to your push. It's parallel to the surface again and going opposite the motion. The last case, we push a heavy object that doesn't move. So even as I'm applying different amounts of force to my desk, it's not moving. So since it's stationary, there must be an equal and opposite force that's pushing back on me. If I push harder, the opposing force must also increase because it's still not going anywhere. Eventually, the opposing force will reach a maximum though, and that's when I can finally get the desk to start moving. I'm not going to do that now because I want to keep my computer on my desk. But there is some limit here, which is interesting. It matches my applied force up to a point, and then it can start moving. And this brings me to a question I want you to be thinking about in this section. And that's, why is it easier to push an object once it's already moving, right? It's hard to get that desk to move, but if you can just get it started, then it's a lot easier to keep it moving. So why is that? Well, to answer that, we're going to need to take a closer look at friction. So it turns out there's 2 different types of friction. There's the static frictional force, which we often just refer to as static friction. This is the opposing force that prevents an object from moving or sliding. So it can have any magnitude from 0 up to a maximum value. Once the maximum is reached, then the forces are no longer in equilibrium and the object will start to slide. Once it's sliding, kinetic frictional force takes it over. So kinetic friction is the opposing force that acts on any object in motion. It's very similar to our air resistance or drag, which we are going to see in just a moment. Kinetic frictional force only has one value in contrast with static friction, and it's generally smaller than the maximum static frictional force. That's a key clue there. So we could look at this in practice with a block, and if it's just sitting there, gravity's pulling it down and the floor is pushing back on it, and so the forces balance out. None of those forces are trying to move the block. Since there's no attempted motion, the frictional force is 0. But let's say we start trying to push on the crate, right? So if I start trying to push it on the crate, up to some point, the crate won't immediately move, right? If I'm just like barely pushing on it. And so the frictional force is going to match my applied force, but in the opposite direction. That's what's shown here, where the two vectors are equal and opposite. We can start pushing harder, right? Using more fingers. The frictional force will continue to match that. You can push harder and harder, right? And it will keep matching that even as you're pushing harder and harder up to some point. What point is that? Well, once you reach that maximum static friction force, then there's this breakaway where the applied force is just enough to overwhelm the static frictional force and the object starts to move. As soon as it's moving, it becomes the kinetic frictional force. So notice there's a subscript of K there. This is a little hard to see, but this is the notation we use for kinetic friction is lowercase f sub K versus the static friction is lowercase f subscript s. So once you get it moving, right, with that large applied force, if you want to maintain the speed, just keep it going at a constant value and not keep an acceleration, because notice there is an acceleration drawn in here. Well, then you can reduce your applied force, and all you have to do is match the relatively weak kinetic frictional force. So this is shown on this graph here, that time and as force increases, the magnitude of the frictional force is going to increase. It's going to go up and up and up to a point, up to that maximum value of the force of static friction. At that point, the object breaks away and starts to move, and the friction value drops and then stays relatively constant for the entire motion of the object. So it only has one value. It does not match your applied force, unlike the force of static friction that does match your applied force. So this can give you a bit of a clue as to why it's easier to push an object once it's already moving. Something to think about there. All right. Now, let's take a closer look at friction. So in the microscopic picture of friction, it arises because surfaces are actually bumpy, even ones that seem super, super smooth. Friction occurs as those contact points slide over each other. But it's possible to prepare two metal surfaces to cold weld together and become impossible to slide because there's so much contact between the surfaces. So this is something that can be done. There's a couple videos here. Here's an example of two pieces of metal that are just pressed against each other. There's no glue applied, no adhesive, but they're just smoothed out and pressed to remove any of the air from between them, and then they stick together. This is also a problem in outer space. It's why none of the tools that are used on the outside of the International Space Station are made of metal, because if they were made of metal, then they could just stick to the spaceship. And then that's a bummer, because then you no longer have your hammer or whatever your tool is. So it's something you can look into. That's a bit of an aside. If you have greater force normal to the contact plane, that'll increase the friction because the surfaces are pressed together and they make more contact than if they're barely touching each other. They don't make as much contact versus pushed hard together. You can feel it with your hands. Sliding is jerky due to ridges on the surface produces the squeaking, squealing sound, right? You may have heard this opening a creaky door, right? Really obnoxious, right? What do? You get some WD-40 in there, and that lubricant goes between the ridges on the surface and it smooths things out so that we don't have friction, or we have less friction, And so we don't have to deal with that squeaking, squealing sound. Pretty great. All right, now that we've taken that close-up look at friction, let's look at the properties of friction, which will give us an idea of an overview. So first, if the body does not move, the applied force and the frictional force balance along the direction parallel to the surface. So they're equal in magnitude, opposite in direction. Okay? So that's, okay, perfect balancing. The magnitude of this force of static friction has a maximum, and that's given by this equation, that Fs max is equal to mu s times the normal force, F sub n, where mu s is the coefficient of static friction. If the applied force increases past this maximum value of friction, sliding will begin. And notice the normal force is in here because that tells you about how much the surfaces are pressed together. If they're pressed together more, we have more friction. This coefficient we're going to see some examples of in just a minute. It comes experimentally is how you derive it, so it'd be given to you in a problem. All right, so once we increase past this max value, sliding begins. As soon as we have sliding, the frictional force is going to decrease to the force of kinetic friction, which is given by the coefficient of kinetic friction times the normal force. So the magnitude of normal force, once again, measures how strongly the surfaces are pushed together. That's why it appears in both of those equations. Values of the friction coefficients are unitless, and they must be determined experimentally. We're going to assume that mu sub k does not depend on velocity, which is reasonably true. And note that these equations are not vector equations. So even though we have that the force of kinetic friction is equal to a coefficient, mu sub k, times the normal force, we do not have arrows above because the force of friction is not in the same direction as the normal force. In fact, they're always going to be perpendicular to each other. So the force of friction is always going to be along the surface, while the normal force is always perpendicular to the surface. So that's something you want to be careful with. Right, let's look at some of those coefficients of friction. So here we can see the coefficient of static friction and that of kinetic friction. This is a table from another physics textbook. And what you'll notice is that the coefficient of static friction is always greater than or at most equal to the coefficient of kinetic friction. That's why static friction has a larger value. That's why it's harder to get an object to start moving than to just keep it moving. It's a stronger force. So yeah, you can see some examples here, wood on wood. If you have two pieces of wood sliding against each other, coefficient of static friction 0.4, kinetic friction 0.2. Again, this is just a unitless number that you plug into that equation. But down here, lubricated ball bearings is less than 0.01. That's reduced a lot of the friction. And synovial joints in human limbs are very similar to those ball bearings, which is great. We don't want to have a lot of friction involved in trying to move our bodies. So that's a great thing. All right, let's look at a checkpoint here. It says a block lies on a floor. What is the magnitude of the frictional force on it from the floor? If a horizontal force of 5 newtons is now applied to the block, but the block does not move, what is the magnitude of the frictional force on it? If the maximum value, Fs max, of the static frictional force on the block is 10 newtons, will the block move if the magnitude of the horizontally applied force is 8 newtons? If it is 12 newtons, what is the magnitude of the frictional force in part C? So there's a number of parts here to analyze. I want you to think through each one, come up with an answer to them, and then you can go on to see the results. So go ahead and pause the video now to think about it. Alrighty, so magnitude of the frictional force from the floor. Well, if it's just sitting there, there's no friction. We only have a frictional force when something starts to get pushed, right? When we have this horizontal force of 5 newtons, then we can look at the magnitude of the frictional force. Since the block does not move, we know that the frictional force is going to be a matching force. It's going to have to be exactly 5 newtons for part B here. Part C, if the maximum value is 10 newtons for Fs max, will the block move if the magnitude of the horizontally applied force is 8 newtons? Well, is 8 greater than 10? No, not so much. So no, it's not going to move. What if we apply 12 newtons? Yes, in this case, that is greater than Fs max, so that is going to be moving now. We have overcome the maximum static friction. what is the magnitude of the frictional force back in part C? Well, in part C, it is not moving, so that is our applied matching force, right? Static frictional force will match, so that will be exactly 8 newtons. In part D, when it's 12 newtons, we know that it is now moving, and so we no longer know what the value of the friction is. We'd need to have more information, because it's going to be the force of kinetic friction, but it's going to be something less than 10 newtons most likely. So that would be a little more information needed if that question were to be asked. All right, so pulling this all together, we have 0 at first, 5 newtons, then no, yes, and 8 newtons. So that does check out. That pulls us through the section on friction. I hope that you enjoyed and did not find it too rough.